Good afternoon, everyone. I'm Momita Sarkar. I'm a PhD student at the Department of Wind Energy in Technical University of Denmark. And today I'm going to present my paper on impact of wind power plants on voltage control and of power system. So with increasing renewable energy sources in traditional power systems, more and more conventional generators are being replaced by converter-connected generators. The graph here shows the substantial amount of RES are present in a lot of European member states. For example, in Denmark, it is 36.8%. So with such increasing renewable energy sources, power systems are becoming weak due to low short-circuit power available in the system and also due to low system inertia. So such weak power systems, together with variability of wind speed, can cause voltage fluctuations in the system, both in transient conditions and also it can cause poor steady-state voltage profile. So this provided the motivation for this work. So for this work, we modeled type 4B wind turbine model as proposed by the International Electrotechnical Commission, IEC, in their report IEC 614-00-27-1, Electrical Simulation Models of Wind Turbines. Well, I'm not going to say much about the IEC models, as Professor Paul Sorensen here will discuss the IEC models in details in the late afternoon session. So I'm just going to say a brief overview of the type 4B model only. So type 4B IEC model was proposed to study transient stability issues. But we wanted to extend this model such that the variability of wind speed could be incorporated in our model. So we added the wind speed block, pitch controller block, aerodynamic block, and MPPT block in this model. Rest of the blocks, the mechanical model, the controllers P and Q control, and the static generator model are similar to the IEC model. So I'll come to each of the blocks now. So starting with the pitch controller block. So the pitch controller block consists of a anti-wind-up PI controller and a servo mechanism with pitch angle and rate of change of pitch angle limitations. So what this block does is, during high wind speeds, when the generator speed limit is reached, the rotor speed is limited by increasing the pitch angles such that the mechanical limitation of the generator is maintained. And so during low wind speeds, the pitch angle remains at a constant optimal value. So next, the aerodynamic block. So the aerodynamic block, what it does is it computes the aerodynamic power output of the wind turbine based on the wind speed and the pitch angle. This is the formula implemented in the model. So here we can see that this CP, the CP here is the power coefficient, which is a function of the pitch angle theta and the tip speed ratio lambda. So this lambda is actually the ratio of speed of tip of blade to wind speed, which is calculated using this formula. The rest of the symbols here represents the air density, the rotor radius, the wind speed, and this is of course the power coefficient, as I said earlier. This power coefficient has been modeled as a two-dimensional lookup table in this in our model, and this power coefficient, it helps us to see the effect of changing wind speed in the aerodynamic power. Next, comes the MPPT table. The MPPT table, this is for reference. I have put, it looks like it's a 1D lookup table, which looks like this, generator speed versus active power. So what it does is, below the nominal rotational speed, this MPPT table, which stands for maximum power point tracking, it enables us to extract optimal aerodynamic power from wind by making the generator work at maximum power coefficient. So basically, it is a lookup table which looks into the which gives the active power output, or the reference active power output of the generator based on the generator speed. So next comes the mechanical block. The mechanical block has been implemented as a 2-mass model, and this is similar to the mechanical block proposed by IEC in 6140027-1. So the parameters considered in this model, in this block, are the stiffness and tamping of the shaft, as well as inertia of the rotor and the generator. So what this mechanical block is capable of is that it can capture the oscillations due to sudden wind gusts or sudden changes in active power set points. The active power control block implemented here is a very simple one with a anti-wind-up PI controller and a low-pass filter. This is a bit different from what has been proposed in IEC models. So this measurement filter has been used such that the high-frequency fluctuations in the measurement can be filtered out. Next comes the reactive power control block. So this is similar to the IEC proposed reactive power control block, which is capable of being operated in different control modes, such as voltage control, reactive power control, power factor control, and as well as open and closed loop control. So this also consists of an anti-wind-up PI controller as well as a low-pass filter. So what it does is, when the measured voltage is less than the threshold voltage, then this LVRT detection block detects that fault has occurred, or something has occurred in the system and the voltage has gone down than the threshold voltage. So LVRT signal is generated, and the controller works in LVRT mode. So what according to the Danish grid code, reactive power delivery is prioritized during short circuits or during voltage dip conditions. So what is done here is that a voltage scaling factor is used to determine the LVRT current, reactive current contribution due to voltage dips. Also, there is provision for post-fault current contribution. Some grid codes require that a certain amount or reactive current is injected for a specified post-fault period. So IEC model also has provision for this one. Next comes the static generator block. So this is also similar to the IEC model, and we have implemented a current limiter model along with a phase lock loop and a static generator block. So the input to the generators are the reference active and reactive currents and the PLL information. So to see the performance of this extended type 4B model, we did some tests, and for this we chose a very simple model, a 2-bus model. So the wind turbine here is connected with the external grid via a step-up transformer. So we did 2 studies. Firstly, we did step changes in wind. So what we did is we increased the wind speed from about 6 to 18 meter per second with a step change of 1 meter per second every 30 seconds, I guess. I'm not sure. Yeah, I think so, 30 seconds. Okay. So we can see that, by the way, the rated wind speed for this one is 12 meter per second. So, which is around here. So we can see that the active power increases as the wind speed increases until the rated wind speed is reached. Along with the active power, the generator speed also increases until the rated wind speed is reached, but the pitch remains constant at low wind speeds. When when the rated wind speed is reached, the active power and the generator speed becomes constant. But now the pitch control mechanism comes into action and the pitch angle starts to increase so as to limit the rotor output such that generator remains within its speed limit. The next test that we did was step changes in reactive power set point in Q control mode of the Q controller. So what we did is we provided step changes in the Q reference set point, and we can see that until here the reactive power output from the controller follows the Q reference set point accurately, but here the controller limit has been reached, so even though Q reference is being lowered, the reactive power output doesn't change. And according to the reactive power, the voltage at POC is also changing, but in this region it is constant. But we can see that the active power remains constant throughout this study. This is because type 4 wind turbines are connected to the grid through back-to-back fully rated converters, which makes it possible to decouple the wind turbine generator from the grid, and also it helps or it assists in independent active and reactive power control. So next, to do the voltage stability studies, we incorporated the wind turbine model in an aggregated form to this test system. This is an academic system developed at Technical University of Denmark, mainly for voltage stability studies. So what it has are 4 central power plants, and with this system, a wind power plant of 300 megawatt has been added at this end, and it is connected to the system through this long 150 kilometer long transmission line at this bus. So to do the studies, what we do is we do a 3-phase short circuit in this line, and to clear the short circuit, this line is opened such that the system becomes stressed. So this bus is prone to voltage fluctuations, and this bus voltage has been observed. So with this long 150 kilometer transmission line, the short circuit ratio calculated here comes to about 1.52, which as per IEEE definition corresponds to a very weak system. So we did transient studies as well as steady state studies on this system. So first and for the limitations, the current and voltage limitations of the model, we referred to the Danish grid code as from energinet.dk. So this is the transient requirements of the Danish grid codes. This is the voltage dip tolerance requirement. So the wind power plant are expected to remain connected to the grid even in this region. So it is expected to withstand a voltage dip of around 0.2 pu for about 500 milliseconds. As reactive power injection is prioritized during voltage dip, so this is the reactive current injection requirement during faults, and this has to be provided within 100 milliseconds. As for steady state operation, this is the reactive power in relation to the active power requirement, and this one is the reactive power in relation to the voltage at POC. So the wind power plants are expected to be operated within these shaded regions. So for the transient study, we studied the low voltage right through. So we did 3 studies, one without LVRT and one LVRT with the Q controller operating in voltage control mode and the other in the Q controller working in Q control mode. So we can see that without LVRT, the reactive power support from the wind power plant is not that good. So the voltage dip during fault is more than when there is LVRT support from the power plant. Also, we can see that without LVRT, the post-fault voltage recovery takes a longer time, but both V control and Q control modes of operation gives a faster voltage recovery time. One thing can be noticed here is that both V and Q control mode provides equal support during LVRT, but the post-fault steady-state voltage differs a bit because of the reference voltage set point or Q set point. Next, the steady-state analysis. So what we did is we did some power flow, and firstly we operated the wind power plant in V control mode with the reference voltage as 1.04 pu. So in a pre-fault scenario, the voltage at the observed bus, that is bus 111, was 0.95 pu. But when the fault happened and the line got disconnected, the voltage at this bus falls to 0.92 pu. And the reactive power output from the plant was 0.22 pu. So if we could go back to this one, we can see that when there is 1 pu active power output from the power plants, the reactive power can go up to 0.228 pu. So we can see that there is still some potential or some capability of the wind power plant to provide additional reactive power support. But if we are using only local voltage control, probably this capability is not fully utilized. So a centralized secondary voltage control has been proposed, where the capability of the wind power plant is taken into account. And here what we did is in order to get 0.228 pu of reactive power support from the plant, we increased the reference voltage to 1.06 pu, which improved the voltage at bus 11 to some extent to 0.94 pu. So we think that this will help in scenarios, especially when there are large wind power plants connected to the grid through long transmission lines. Also when there are multiple power plants nearby, so we need to see centralized and coordinated control so as to fully utilize the wind power plant potential. So to conclude, I would say that LVRT support from wind power plants are required, especially in systems with low short circuit ratio, such that low voltage dips at POC can be prevented, and also it can help in fast stabilization of POC voltage. Also, during fault, there is V control and Q control modes of reactive power control behave similarly, but post-fault steady-state voltage differs. In a steady-state operation, sometimes local voltage control of power plant may not be able to utilize full capability of the power plant, but so a centralized secondary voltage control has been proposed, but further investigations are required in this respect. Thank you for your attention.